So in this work, we try to simulate spintronic-based neural network. So in fact, to circumvent the limitations of CMOS or more conventional implementations of neural networks, we can implement them using hardware devices. And we do so by using spin-torque vortex nano-oscillators, which are nanostructures that have a strongly nonlinear response to an input signal. So it is based on two physical effects from spintronics, so the spin transfer torque and giant magnetoresistance. And the advantages is that it's low power, low noise. It's well known as it's used in MRAM, for example. It's also CMOS compatible. And we can use the nonlinearity of these oscillators to implement physical reservoir computing, which is a framework when we design a fixed and random neural network to treat nonlinearly input data and classify them. The advantages is that it's easy, it's well known in the literature, and we only have to train the readout layer of the network here, and this can be done linearly using a standard least square regression. So to simulate such a network, to avoid manipulating a lot of nanostructures, we simulate the network using a custom model. So the model is an analytical description of the dynamics of the oscillators that allows to transform a given input signal into a feature vector that will be used to train this readout layer and perform recognition. So this can be seen as an activation function that is described by the physics. We tested this framework using our simulations on many tasks. So for example, here on waveform recognition, so the classification of sine and squares function, this model allowed us to perform extensive parametric studies, for example, by varying physical operating parameters of these oscillators. So for example, the amplitude of the input signal, the level of noise in the systems. We also show the consistency of this model with experimental results during speech recognition, so the classification of digits from 0 to 9 spoken. And it has a very good consistency with experiments. And we also showed that it was efficient at classifying rhythm digits with the MNIST dataset. And actually, we can compare this function described by the dynamics of this oscillator with standard activation functions such as the ReLU, the sigmoid, and we show that it's equivalent at a large number of parameters. So here we showed how we can train this network to recognize rhythm digits. So the framework is actually really simple. And to conclude, this new model called DDTA is an analytical description of the dynamics of spin-torque vortex nano-oscillator that allows a fast and accurate description of the dynamics. And we use this model to assess the influence of operating condition of physical reservoir, but also the consistency with experimental results and the comparison with the literature and already known activation functions. So the perspectives are the study of more complex architectures, but also an efficient preparation of an actual experimental network. Thanks.